Before we proceed on using matrices in solving systems of linear equations, let us first discuss the properties and operations involving matrix or matrices. So a matrix is a rectangular array of scalars in the form shown. So we have here Aij being an element of the matrix A, where I is the row position from the top and J is the column position from the left of our matrix. M is the number of rows in the matrix A and N is the number of columns. The shape or size of a matrix is defined by M by N. If M is equal to N, then it is called a square matrix. We have here a matrix A and its size is 2 by 3, 2 rows and 3 columns. Another matrix B has a shape of 3 by 2. It has 3 rows and 2 columns. Matrix C is an example of a row matrix because it is composed of only one row, regardless of how many columns it is composed of. Matrix D is an example of a column matrix. It has only one column, regardless of how many rows it has. Equal matrices. Two matrices are equal if and only if, first, they have the same shape, and second, all entries corresponding must be equal. The matrices would be considered equal if it satisfied both of these conditions. Let's have an example. We have here matrices A, B, and C. As we observe, all of these matrices have the same shape, 2 by 3. But if you will observe, for matrix A and B, we have here an element A2, 3, 6, and for matrix B, an element A2, 3 of 7. So although they have the same shape, it did not satisfy the second condition, which is all entries corresponding must be equal. So A and B are not equal. But for A and C, we have here the same shape and all entries corresponding are equal. So we can say that the matrix A and matrix C are equal. For matrix addition, we have one condition. Matrices with the same shape can be added, otherwise the sum is undefined. So, for matrix addition, we first determine the shapes of our matrices before we add them, because you cannot add two matrices of unequal shape. For this example, matrix A and B, if you are going to take the sum of these two matrices, since they have the same shape, we can add this up. So, the sum of these matrices is just equal to the one shown below. And also, one property in matrix addition is that it is commutative. A plus B is equal to B plus A. Next is scalar multiplication. For scalar multiplication, each elements or entries in the matrix is multiplied with a given scalar quantity. For example, we have here matrix A as shown, and we are asked to find 7A, where 7 is a scalar quantity. So 7A, we are just going to multiply the scalar quantity 7 by each of the elements of the matrix A. We now have 7A is equal to the matrix shown below. For matrix multiplication, let's recall the dot product of vectors. We have here a row vector and a column vector B. The dot product of these vectors is equal to 1 times 4, 2 times 5, and 3 times 6. Adding this up will yield to 32. That is the dot product of the vectors, similar to row times column multiplication. This is generally the process on how to solve the product of matrices involving many shapes. We have here a given linear system. In matrix equation, it can be written as follows. So the matrix in yellow is called your coefficient matrix. The matrix in red is called the column matrix of variable. The matrix in blue is called your column matrix of constants. So the shape of the product is determined by the shape of the two matrices being multiplied. So for the coefficient matrix, we have a 2 by 2, 2 row and 2 columns. And for the column matrix for the variable, that is a 2 by 1 matrix. So for a matrix product to be defined, the number of columns of the first matrix and the number of rows of the second matrix should be the same or equal. The number of rows of the first matrix and the number of columns of the second matrix defines the shape of the product of the matrices. So for this one, called matrix A and B, the product is defined if P is equal to Q. And the shape of the product is M by N. Okay, let's have an example on how to find the product of two matrices. So we have here matrix A and matrix B. If we are asked to find matrix A times B, so the first step in matrix multiplication is to find or determine whether the product would be defined or undefined. So that would be, for the first matrix, it has 3 or 2 rows and it has 3 columns. So that is a 2 by 3 matrix. For matrix B, it has 2 rows or 3 rows and 1 column. Since these two numbers are equal, then the product is defined. And the shape of the product of these two matrices is determined by these two values. The product then will be 2 by 1 matrix. So for AB, that is equal to row by column multiplication. So that would be 2 times 0 plus 1 times 1 plus 0 times 3, and for the next one, that would be 5 times 0 plus 2 times 1 plus 3 times 3. So this is equal to 0. 1 times 1 is 1. 0 times 3 is 0. So for the first element, that is equal to 1. This is also 0. This is 2. And this is 9. That is 2 plus 9 is equal to 11. So we have here the product of our matrices A and B. So it is defined. Indeed, the shape of the product is a 2 by 1 matrix. It has 2 rows and 1 column. What if you were asked to find BA, or the product of matrix B and matrix A? So, for matrix B, it has a shape of 3 by 1, 3 rows and 1 column. For matrix A, its shape is 2 by 3. Since these two values is not equal, then the product is undefined. You can do this process for any shapes or sizes of matrices. You will just need to follow the process of row and column multiplication. Let's have another example. We have here matrices A and B. If you're asked to find A times B, so the shape of matrix A is 2 by 3. The shape of matrix B is 3 by 2. So these two values are equal, meaning the product is defined, and the shape of the product of these two matrices is equal to 2 by 2. So let's try to find the product AB. That would be 2 times 0 plus 1 times 1 plus 0 times 3. And then, for the next element, that would be 2 times 2, 1 times negative 1, 0 times 0. Next, we have 5 times 0, 2 times 1, 3 times 3, 5 times 2, 2 times negative 1, 3 times 0. So this is 0, 0, 0, 0. So for the product AB, that should have a shape of 2 by 2 matrix. So this is the first element, or element A, 1, 1, in the first row and in the first column. That is 1. A2, 1 for this one is equal to 11. For A1, 2, that is 2 times 2 is 4, minus 1, that should be equal to 3. And for the last element, or last entry, this is A2, 2. That is 5 times 2 is 10, minus 2, this is equal to positive 8. So we have the product AB as a 2 by 2 matrix, true to what is shown in this property.